Hello, this is a Unit 7 review for the final exam of ENGR 201. So here we'll be going over a little bit of line integrals, a little bit of Green's theorem, a little bit of a surface integral. So now we need to verify the circulation curl form of Green's theorem. So we need to use a line integral to prove the area integral. So for the line proportion, again, we only have this one line. So if we had multiple lines, then we need to break it up into multiple segments. But since we only have this one flow of equation x squared plus y squared equals 4, we don't need to worry about breaking this up into multiple line integrals. But it is prompting us to solve for x, y, dx, and dy. So looking at this, it's x squared plus y squared equals to 4, which we can Englishly distinguish that as r squared equals 4 or r equals to 2. So we know that this is right here is r equal to 2. And this more likely means if we're doing area integral, it's probably easier to solve for this using polar coordinates. So we're going to have to solve for x, y, and dx, dy in terms of polar coordinates. So again, remember x is r cosine theta. In this case, r is 2. So 2 cosine theta. Y is 2 sine theta. Dx is going to be the derivative of 2 cosine theta, so it's going to be 2 negative sine theta d theta, whoa, d theta. Dy is 2 cosine theta d theta. And then the line integral for circulation, remember, is f dot dr for the line integral. So f dot dr, or mdx plus n dy plus p dz. There's no z in here, so I'm not going to include it. Remember, here's our f, xyi plus xj. So then that means when you plug this in, this will be the integral of x, y, dx plus n, which is x dy. So we substitute all of our stuff in. So it's the integral of x, so 2 cosine, y is 2 sine, so, and dx is negative 2, so we're going to have a negative 8 here. We have 2 sines, so it's going to become cosine theta, sine squared theta, and then plus x, which is 2 cosine theta, and dy, which is 2 cosine theta, so it's going to become 4 cosine squared theta, all times by d theta. Our limits for theta are going to be from 0 to 2 pi. So when we solve for this, again, we can make this our u, this our du. So the first integral is going to be negative 8 over 3 sine cubed theta from 0 to 2 pi. And then before we can integrate this term here, we must substitute in for the half angle formula, which is integral. So we have the integral from 0 to 2 pi here still, and it's going to be 4 over 2 theta 1 plus cosine 2 theta, all times by d theta. So this sine term here is going to go to 0 because sine of 2 pi is 0 and sine of 0 is 0. So this is going to go to 0 anyways. Now when we integrate this, we're going to have 2 times theta and sine over 2 theta from 0 to 2 pi. Like I said before, sine goes to 0, so this goes to 0. So we have just 2 pi. We have this theta here, so it's going to equal 2 times 2 pi minus 0. Which equals 4 pi. Now the area integral here, so remember circulation curl form, the stupid mnemonic device I have is Nixon stole my curling iron. So Nixon being partial of n partial of x, stole being minus partial n partial y for my, and curl, because remember it's circulation curl form, and this is going to be dA xy. So partial of n with respect to x is going to be 1. and the partial of m with respect to y is going to be x, and dA is just going to be d theta, it's going to be r d theta, because again it's going to be we'll leave it as dx dy, and then we'll substitute in for r and theta, so it's going to be 1 minus, remember cosine is 2 cosine theta, and then we'll have r dr d theta. R is going to be from 0 to 2. Theta again is from 0 to 2 pi. We're going to integrate r, so it's going to become minus 2 cosine theta. It's going to become r squared over 2 from 0 to 2 d theta. So it's going to become 4 minus 0 over 2. So it's going to become just 2 overall. So it's going to equal to 2. Integrate theta. So it's going to become 2 times theta minus 2 sine theta from 0 to 2 pi. We'll have this term will go to 0, and then again we'll have 2 times 2 pi minus 0, which equals 4 pi. It's the same thing. Therefore, I've verified circulation curl form for Green's theorem. All right. So now I need to find the outward flux across S equals S1 plus S2, where F equals Xi plus Yj plus Zk. So F of Xy for the first surface, which is Z equal to 4, which is also coincidentally the answer. Because again, we want to make sure that our n hat is in the right direction. So n hat here is going to go straight up. So we need to make sure that Z is positive. So when we do del F, we want to make sure that we get a positive K here, which we do, because we do the partial of the F with respect to Xi, which is 0, Yj, which is 0, and then Z, which is 1 times K. Now n hat d sigma, remember that is del F over magnitude, in this case Fz dAxy, which will just equal K dAxy. Now we're going to do F dot n hat d sigma. So F for here is Xi plus Yj plus Zk. Only the Z's are able to be dotted because everything else is 0. So we'll have Z dAxy. So now we're going to do a double integral of Z dAxy. But we have to make sure that it's all in terms of, because again, this we're going to have to solve for the area of this. So looking at this from the top down, we're really looking at something that looks like this, where R, so we need to figure out what that R is. So if Z equals 4, and we're looking at this equation here, so we have 4 over 4, which equals x squared plus y squared, which equals r squared, which means r equals 1. So we have a circle here. So if we have a circle, then we're definitely going to be using polar coordinates. So we have the double integral of z dAxy, which then becomes, and again, we can have z here, but we know that z equals to 4. So this becomes a double integral of 4 r dr d theta, and then r is from 0 to 1, and then theta is from 0 to 2 pi. Integrate, and it becomes 4 over 2 r squared d theta. This is from 0 to 1, which is just 1. So we have it equals 2. Integrate, we have theta, 0 to 2 pi, which then this equals 4 pi. And now we need to solve for S2. So S2, this is what our n hat's going to be. It's going to be going in the downward direction. So since this is n hat 2, this is n hat 1. So our n hat 2 in this case is going down, is going to have a negative z. So we need to make sure that when we use this surface here, we get a negative z out of it. So it's going to become, I want to multiply that 4 out, 4x squared plus 4y squared minus z equals 0. So that's my function that I'm going to be using to solve del f. So del f is going to be 8xi plus 8yj plus, no, not plus, but minus z, or the partial z with respect to z, which is just k. So now n hat d sigma, remember that is del f over f, the magnitude of fz. In this case, it's fz, but you can have other cases where it's not fz. They will probably prompt you which one you have to use depending on what they give you. So in this case, we have yx here. Z is missing from that plane, so we have to use fz. So we have daxy, which then this will just equal 8xi plus 8yj minus k daxy. Now I need to do f dot that. So it's xi plus yj plus zk is f. So this becomes 8x squared plus 8y squared minus z daxy. So I know when I go to plug this in, I can reduce this x squared, because again, we're going to be in polar. So x squared plus y squared can come to an r squared, so it becomes 8r squared. Z, go back up to z. We need to figure out what we can plug z in as. So z, if we were to solve for z over here, again, use the surface. So z equals 4x squared plus 4y squared. So we can plug in essentially 4r squared into here. So we have minus 4r squared dA, which is r dr d theta. So this will equal a double integral of 4r cubed, because again, these will cancel out to be 4. And you have multiply this r here, so we have r cubed. And then our r's are going to be from 0 to 1, and our thetas are going to be from 0 to 2 pi dr d theta. So then this will equal r to the fourth over times 4 over 4, so it becomes r to the fourth d theta, 0 to 1, which is just going to be 1. So this equals the integral from 0 to 2 pi of d theta, which then equals theta from 0 to 2 pi, which equals 2 pi, which makes the whole thing equal to 6 pi. So now I need to, yep, okay, that's it. There's more to the problem, but that's it. So you add up the two s's together to get the total surface integral for this. And note that you remember that your n hat keeps track of your direction. So if you were using a surface integral, remember your surface integral just cares about area. So your n hat should keep track of your direction. So if you would happen to pick the wrong direction, say we picked minus here, we check the minus one, then we need to make sure we flip our limits. So make sure you choose the right n hat, then all you have to do is just solve for area like normal, and you don't have to worry about directions or anything else when it comes to limits. All right, is it for Unit 7, and good luck.